leaders inspire others to dream more, learn more, do more, and become more. It is my privilege to invite Dr. C. Janita Nancy, Assistant Professor, Department of Mathematics, PPG College of Arts and Science, to formally introduce our esteemed speaker of the day.
Thank you, ma'am. Our speaker of today, Dr. Albinaa, is a distinguished individual with a strong academic background in mathematics, having earned a PhD in mathematics with a specialization in intuitionistic topology. With experience in teaching, research, and academic leadership, Dr. Albinaa has held notable positions such as Secretary of Extension Activity and Vice President of the Maths Department at her college. Her achievements include guiding data analytics projects, delivering guest lectures, and participating in conferences. Dr. Albinaa is currently a manager at Maria Christu Cargo Movers, Coimbatore. Her expertise in applying mathematical concepts to real-world problems and contributions to the field of intuitionistic topology make her a respected figure. We look forward to her insights and sharing her knowledge with us today. Welcome you, ma'am.
Thank you, ma'am.
Thank you, ma'am. Education is not the filling of a pail, but the lighting of the fire. Now, I request Dr. Albinaa, Manager, Maria Christu Cargo Movers, Coimbatore, to lead today's session and share her expertise with us. Welcome, ma'am.
Yes, ma'am. Ma'am, am I audible?
Yes, ma'am.
Yes, ma'am. Yes, ma'am. You're audible.
Yes, thank you, ma'am. Very good evening to one and all present here. Yes, first of all, I would like to thank God for this event, and I also thank the faculty and management for inviting me for this faculty development program. I also extend my hearty thanks to Madam who rendered the welcome address. At this juncture, being invited to the talk of today's session, and the topic is based on AI techniques like machine learning empowered by mathematics. The literal meaning when we go on to machine learning empowered by mathematics, it is nothing but here max is the foundation and it is also the toolkit that enables machine learning algorithm. So that is the base which we are going to deal here. And what happens here is we learn, we optimize, and make intelligent decision from the data. So we are here to know that Max is the foundation and toolkit for machine learning. Yes. So that is the core knowledge or the idea for today's session. Instead of simply applying the pre-packaged code, being mathematically empowered allows deeper understanding. So when we are mathematically empowering, so we were just going to know what is being done there in depth and how it controls or how it works and why an algorithm works. In spite of the code, we are going to deal with the mathematical background in it. And even more, when I have to tell about the topic, it is nothing but since it's a mathematical empowerment, I can say the core pillars here, which deals with the subject knowledge, is nothing but you can see some fields like linear algebra, calculus, probability and statistics, information theory. All these are the fields which work together to what to say to make machine learning models wonder. Okay, so these are the things done here. And as we have all seen about linear algebra, all those previously, today I'm here. I'll be taking a model in probability and statistics, and I can help you give some ideas and discuss some topics here. Sir, kindly switch over the slide. Yes. So when I told about the probability and statistics, I'm just considering a particular theorem named the Bayes theorem. So I'll just first give a gist of what we are going to deal with today, and after which I'll just start with the Bayes theorem. going with the topic, I just wanted to give some ideas in max and then related to the same thing, how it is working in machine learning. And so we can say that machine learning is empowered by mathematics. So that was my base idea to deal with. And while selecting the topic, I just thought of going with Bayes' theorem. We would have heard about it. We would have heard about it in theory sense. Just now, I'll just deal with a small concept apart from mathematics. So first, we'll just know what is a Bayes' theorem. And after that, we'll just go into max, saying what is Bayes' theorem. And after which, I'll be telling Bayes' theorem in machine learning, otherwise called the Navy Bayes. So this is my just a gist of what I'm going to deal with today. Yes, as the topic here in the slide is mentioned as I've given is Bayes' theorem. It is nothing but we have seen this in some parts and some applications also in probability and statistics we would have dealt with it. And the base or the formula for this, it will be given as probability of A given event B equal to probability of the event B given A into probability of A divided by probability of B. While considering the left hand side, you can just see that I would have mentioned it to be a posterior probability. So when you say it to be a posterior probability, and when I'm reading this particular term, I can just read it as probability of event A given B. So why I'm saying given B is nothing but here I'm focusing on the occurrence of the event A. So event A is going to happen now. So that is the thing which I'm going to concentrate. But the event B would have occurred already. So that's why I'm saying that it is given B. So we usually read it as such. Probability of A given B. So, and I also call it as the posterior probability. Why it is nothing but it is the thing which you are going to find based on the data or evidence collected. Okay. And when you say about probability, we people know it is nothing about handling uncertainty, and we come make some decisions and come to your conclusions. So that's what is happening here also. So when we are considering your right hand side, it is nothing but your probability of event B given A. And it's called the likelihood property probability. Why I say it to be a likelihood is nothing but here is the place where you put all the evidence or data is collected there regarding your evidence. So all that will be substituted there, and that's why it's called as the likelihood probability. And next one, probability of A is nothing but the prior probability. We say it to be the prior since, or otherwise you can also say it to be the initial probability. So it is the name such. And you are giving a denominator probability of B, otherwise the normalizing constant. So it does all the normalizing work here. Next. So as I already told, I'll just tell you what is Bayes' theorem apart from mathematics. So I'm just giving a scenario here. We recently saw the formula for Bayes' theorem. So now when I'm giving a scenario, it is nothing but I'm having a friend named Bob here. Okay. So I'm just giving this fellow here and I'm naming it to be a friend, and he is Bob. Just okay. So now being his classmate, what is the feeling is that this fellow is an introvert guy. Introvert in the sense we just don't make friends or being up to his own self, not getting into others, friendly or anything like that. You can just keep it. So that's why I have been mentioned here. So who often keeps to himself, I've just given there. We believe that he does not like making friends, and hence I've given the word to be as introvert guy. So I'm just concentrating on this particular person. I'm saying that this Bob is is the main character here, and I'm saying that his characteristic is introvert. Next. So here, as mentioning the characteristic of Bob, I am denoting him to be P of A or the probability of A. And I'm calling him to be the prior probability. As I told initially, it is nothing but prior, or otherwise I can say it to be initial probability. That is, we are starting with this particular probability, isn't it? So I can name it like that. And in this case, we will call it our assumption that Bob rarely likes to make new friends. As we said, it is an introvert. And now when he is going to college, he comes to meet one another person named Ed. So what is the difference here is that unlike our friend Bob, Ed is a person who's making new friends. He's very eager in making new friends. So you can say two peers in a pod, isn't it? It's something like that. So this is the another person with this particular characteristic. So this Bob is meeting Ed. So when he is meeting Ed, and I can say that I'm assuming my probability of Ed to be probability of B. So the event B occurring is probability of B. In this case, probability is, it is nothing but it is Ed is being friendly. So this is the case over here. So when Bob meets Ed, what's happening is we usually say, people say, friends say, students say, friends of friends, we say. That is nothing but we have a friend and that person have a friend. So being friends together, spending time together, spending days together, we possess the characteristics of the other fellow also. So it is being like this, and what's happening, being with Ed for certain time or certain period, Bob also is possessing the character of making friends. Okay, so it is slightly coming. So he is also evident to that particular characteristic. So now what I'm saying is becoming friends is representing the probability of B given A. So mathematically, when I have to talk about this term, it is nothing that but probability of B given A is B occurring now and A has occurred already. So that is what we are saying. It is making friends now. That is probability of B, and A occurred already is nothing but Bob who does not make friends now, that particular event which occurred in the past. So this is this particular probability. Or otherwise, I can say that based on my theorem, it is the likelihood probability or the evidence. Next. So now looking at your right hand side based on your particular Bayes theorem statement, I can establish my findings as such. So in the left hand side, what I had was the thing which I am given down only. Posterior probability was it was the thing which I had to find, or it was the probability which I had to find. So that is the thing highlighted below. And right hand side, we based on the theorem, what we had was it was nothing but your likelihood probability and the prior probability. So when you are just multiplying both together, so your numerator represents the probability that Bob was friendly, P of A, and being friends with Ed, so probability of B given A. So initially we started with Bob, and when this particular person, when he met Ed, and he possesses the characteristic of him, and this being the evident probability, you're finding your respective probability. So this will be your left hand side. Next slide. So it is just the extract of what we have discussed now. So I just wanted a just glimpse of what is a Bayes theorem as a story. So I just started with probability of A, assuming that the Bob is introvert. So that was my assumption. And when I had one evidence that he's making a new friend with Ed, so he's possessing the characteristics slightly by Ed. And now what is the updated assumption is that he also becomes now slightly introvert. So that is I come to conclude that he also is possessing the characteristics of making friends better than before. Yes. So this is your probability, posterior probability finding based on this particular scenario. Next. So now talking about the application of Bayes theorem mathematically. So long I just gave a general scenario and I just built a relationship there. And I am choosing a, what is it, an example or application based on mathematics. So the particular scenario which I considered is predicting vehicle maintenance needs. So we all have a vehicle and we have to do the maintenance. And in order to predict that particular need, I've just given an example here. So what it says is nothing but Bayes' theorem can help predict when a vehicle is likely to need maintenance, given data about the vehicle's past performance, usage, and maintenance history. So here, using Bayes' theorem, when you're going to calculate, what are the things which you're going to consider is you're going to consider the vehicle's past performance, the usage of the particular vehicle, and the maintenance history of the particular vehicle also. So based on that, Bayes' theorem can calculate the probability of a breakdown or the need of repair at a certain time or distance traveled. So when you will know the need, okay, for the main vehicle maintenance, so that is the particular idea here. And as the formula depicts, we should know which to assign as the prior or likelihood or posterior, all that, isn't it? So what we are going to find is nothing but your posterior probability. So what you are starting with is initially named as the prior probability. So here the working is going in this particular manner. So I'm assuming my prior probability. What being my prior probability is that is the general likelihood of maintenance for vehicles of a certain model or age based on the historical data. So given a model based on the historical data, I'm just giving all the maintenance, all that I'm grouping there. So I'm depicting it to be my prior probability. Now when we get into your likelihood, I'm just putting all the symptoms based on the vehicle. So when we go for regular check of a vehicle, you can see some factors like unusual engine sounds, reduced performance, all those. And putting all these factors as my likelihood, moving on, I can say that my posterior probability will be the updated likelihood that a vehicle will need maintenance or experience a failure at a specific time. So that is what we are, or what is the objective or aim, predicting the vehicle maintenance needs. So all these are I am going to predict. So I am putting that in my posterior probability. Next, fitting it to my formulae, I'm having the factors, that is the symptoms. So based on the symptoms only the maintenance of the vehicle depends. So now instead of terms event A and event B, I'm rephrasing my formulae as probability of maintenance given by symptoms, and that can be calculated with the help of probability of symptoms given the maintenance. That is, as we discussed, it is based on the future, I'm sorry, previous work, maintenance work, that into the probability of maintenance, and the normalizing constant here, it will be the probability of your symptoms. So fitting all these values here, we can find this particular example. So when it is up to a fleet manager, he can use this idea in terms to optimize maintenance schedules, reducing the downtime by predicting when specific vehicles are most likely to fail. So the manager can find when your particular vehicle will fail based on the symptoms. And he can do a regular check and prevent that also. Next. So here I have given one more application of my Bayes theorem. This is about optimizing freight and cargo transport. I just chose some of the examples in this manner. Why is it that usually people always see about a disease or something related to health, medical conditions like that? So I just wanted to try a different example or different scenario. So that's why I've just opted like these. And this one previously, since we did our vehicle maintenance, now the second one, I'm choosing a scenario to be optimizing my freight and cargo transport. So here what is the example is the idea will be it is applied to optimize the scheduling and routing of freight and cargo deliveries. Cargo in the sense we have heard no about all the services like ABT service, all that truck load, all that. So you just collect a load and you just go and deliver, and based on that, how we are going to manage your time and how the raw material is being fitted into your particular vehicle. So all that comes under study. And main factors here which makes the schedule perfect is it is based on the weather, traffic conditions, delays, and based on that the probability of a certain route being fast or most efficient can be updated dynamically also. So all these will be some of the factors which play a major role in your cargo transport. So it can be a weather condition, it can be a traffic condition, and based on that it is a delay or it is perfect, all that you can know. So now based on this I would like to assume my probability terms. So, as already informed or already discussed, prior probability, likelihood, and the posterior probability will be here. And prior, since being the initial values, what I have done here is I just fit in the historical data about travel times for specific routes. It can be taken down. And when we are talking about the likelihood, it is about the data based on the weather conditions, traffic, or the road closure, it can be fitted into that. And when you are going to find the posterior probability, it is nothing but the updated probability whether the route will be most efficient or not. As I am taking a particular route for my delivery, then whether it is efficient, whether it will help that particular logistic company and the other end also. So based on that, I can make my decision to plan the route and delivery schedule, all those. So all those can be done here. Next. Next slide. So based on these particular terms, I'm putting into my formulae so that I'm getting the efficient route instead of A given B. I'm rephrasing here also based on my efficient route and the conditions. So I'll be able to get it. So these are the Bayes theorem concepts, and based on my Bayes theorem, I just gave two examples where we can do straight values and manual calculations in a mathematical way. So logistic companies can dynamically update their delivery schedules and routes to ensure time deliveries. So based on that, you can minimize the fuel cost and improve the efficiency also. So based on these, I can also say that Bayes theorem can improve various aspects of transportation, from optimizing routes and managing traffic flows to predict maintenance needs and improve safety. The core idea here is to continue the update of the probability of certain outcomes based on new real-time data, ensuring smarter decision making in a higher dynamic environment like transportation. Next slide. So based on the different scenarios which we are considering, we can just make our decisions. And some more application, it is based on your traffic prediction and traffic flow management. And we can also see something about our route optimization and navigation system, public transport schedule and optimization, and similarly based on your ride sharing and demand forecasting, accident prediction and safety. So for all these, when we are fitting in the data and calculating our formulae for Bayes theorem, we'll be able to find the posterior probability and make our decision wisely. So one thing which we can remember usually or generally is that your Bayes theorem is nothing but a formula for calculating the conditional probability. Based on that, it will be useful for us. Next slide. Then when we move on to the Navy Bayes theorem, so long what we have dealt is I just started with Bayes theorem and I just told why Bayes theorem and what we are doing there and what type of applications can be solved there considering our data. I just gave some few examples there, and I'm now switching on to Navy Bayes. So why I'm switching here is that what is Navy Bayes? Then what is it to do here? Why selecting Navy Bayes theorem? It is nothing but Navy Bayes theorem is the multiple times of operating a Bayes theorem, it will lead you to Navy Bayes theorem. So that is the concept which I have selected my Navy Bayes theorem. And when you go to the literal meaning of Navy Bayes, the word naive is nothing but the strong assumption that all features in the data set are independent of each other. So there we in Bayes theorem, there we consider the factors giving some assumptions. And when we say about the naive, it is nothing but it is the strong assumptions made between the features in a data set. So that is the difference there. When we are operating and when we are concluding, I suppose it will be more clear. And it can also said that Navy Bayes, it assumes the presence of certain feature and it does not affect the presence of any other feature given in that particular class. That is, it is independent. When you are collecting the features, they are independent within each other. So the features will be like that. And finally, we classify and we can just keep. So this is the thing done here. So this is the literal meaning of the word naive. You can say that it is the strong assumption between the features. That is why it is named as naive. So the same scenario which I have considered for my Bayes theorem is given here, but here it will be in detail. There I just, since we all heard about Bayes theorem, I just gave a gist of it, and now when we are going to naive Bayes, I've just given a detailed way. The same topic only, predicting vehicle maintenance needs, but in naive Bayes. So that is the difference here. So when what we are been predicting is that it is the predictive maintenance is one of the most practical applications of naive Bayes. It is being considered in your transportation and fleet management. Instead of waiting for a vehicle to break down or following a fixed maintenance schedule, so that will disturb the system. So in order to avoid that, you are predicting it in prior. So this is done how it has been done by based on a sensor data, usage history, and observed systems. So there can be a question, why naive Bayes? Already you're having a theorem named Bayes theorem. When one is working there, then why should I select the other or something complex or something other than that? So there are some reasons here. So I've done this idle for this task because I can say that it works well with categorical data. So when you say category, it is nothing but your numbers collected or your data collected with the help of groups. So that is being put it into the term categorical data. And it assumes conditional independence between features given the class, which simplifies calculation. So here you can see that the features are independent. They are not dependent on each other. The features which we select or the features which is being considered, you can find that they are independent of each other. And you can also see that it is lightweight, fast, or in the other sense, it is fast and time limited time of usage. So you can say that. Next slide. So the goal here is nothing but I'm just going to predict whether my vehicle needs maintenance or not. So the answer will be either yes or no. So that is the final conclusion, and that final conclusion will be based on the features. So the features which I am going to depict is nothing but the engine temperature, oil pressure, mileage, and the last feature, unusual engine noise. So when you say about the engine temperature, it can be either high or normal. And when I'm telling about the oil pressure, it can be either low or normal. And when it's about the mileage, it can also be high or normal, low. And unusual engine noise can be yes or no. That is it can either occur or noise can be without occurring also. So something like that. Next slide. So I'm just giving the Navy base formulae. The Bayes theorem formulae, which we already saw, it was based on the symptoms and all. And now I am saying it is about the features. So features in the sense there we can just consider several factors, but here you can say you're considering more numbers of features. So that's what is given as features here. And your event A and B is given either by it needs maintenance given by the features. So probability of finding whether your particular vehicle needs maintenance is based on the features. So the left hand side will be your posterior probability, and right hand side it is based on the probability of the features given the data of your maintenance, and the other one is multiplied along with the probability of needs maintenance divided by the probability of features. So your problem is fitted into in this particular type, and when we are finding the probability it will be of two segments. First we'll be calculating for the class whether it needs maintenance, yes. Then for that, what will be my probability? And the second class, whether it needs maintenance, no. So for that particular term also, you'll be finding your probability. So it will be of two works. So this is the thing I've given here. So we have depicted that it has been done for both class. Needs maintenance equal to yes and needs maintenance equal to no. And then finally, what is your value, which is the highest probability. So based on that, it differs. Next slide. Considering an example data set. So here, what is given here is nothing but just a sample data set given for training. Previous slide, sir. So you're having 7 rows where you can find the temperature high and what are the other options. And when the temperature is normal, what will be the other factors? All that is being seen. So one combination, the first combination is nothing but when your temperature is high, you're finding your oil pressure to be low, mileage also to be high, noise to be yes. So when this is the case, the maintenance will be needed. So that's what it's given yes. And the second row, I have been given the temperature high. And for that particular data, the other values regarding your oil pressure term to be normal, mileage to be high, noise to be yes, and then also your maintenance is being needed. So when you're going to your fourth row, you can say that being your temperature high, the oil pressure low, mileage low, noise yes, the vehicle will need maintenance. But the final or the last row where you can see your temperature to be high, the oil pressure normal, mileage low, noise to be no, then your vehicle, whether it needs maintenance, it has been given as no. So this is nothing but the training data. So this particular data is given, and the other temperature, when your temperature is to be normal, what are the different combinations, that also is given. So why we give this data usually is the model learns from this particular data. It trains, and which helps for testing. So with the help of testing, we'll be able to predict. Next slide. So now let us consider our observation. So when you are considering our observation, I'm just telling the temperature being high, oil pressure low, mileage to be high, and noise to be yes. So just consider this particular set. So from this particular data, as we started, I told we have to calculate for the probability for the scenario yes and the scenario no. That is when the vehicle maintenance is needed, and for the vehicle maintenance is not needed. So that's what is given here. We want to compute probability of yes. So yes is the case when your vehicle needs maintenance. And the same thing, what is your observation? I'm just putting it inside. So these will be your features. So as already told by the formulae, temperature, oil, mileage, and noise. And when you're considering your assumption that the vehicle will need maintenance, if it is in the case of no, so that's why I'm saying probability of no given your features, whatever is your feature, the same feature which you are considering now. So it is nothing but temperature, oil, mileage, and your noise. So what has been done here is the new observation which I am considering. I'm just fitting into my probability which I have to find. Next slide. So step by step, when we have to clarify, as we already discussed, we have to put it into our prior probability, conditional probability, and so on. So when you are going to your prior probability, from the table, actually, we had your total records, it was 7. Based on your S, it was 4, and based on your no, it is 3. So probability of an event A, as usual, which we say, it is nothing but it equals the number of favorable cases divided by the total number of cases. So that's why I've given probability of S equals 4 divided by 7. And when it is no, probability of no equals 3 divided by 7. So I'm depicting in this particular manner based on the given values. I'm just fitting it in this way. So now probability of S is 4 divided by 7, and probability of no, it will be 3 divided by 7. So the next probability being the conditional probability. I'm just going with my S case. So for all the different features which I have, the different features which I am having here is temperature, oil, mileage, and noise. So now based on your particular data, when I'm finding my temperature with high and it needs maintenance, yes, it is given by 3 by 4. So kindly switch on to the table, sir. Previous slide. One slide before. Yeah. So here you can see that when you're considering your temperature alone, and I'm saying my feature to be temperature, and which I'm considering is when my temperature is high and it needs maintenance. Yes. So I am seeing that how many times it's been repeated. So on the first row, I can see the temperature is high and my maintenance is needed. Yes. And in the second row also, I can see my temperature is high and the maintenance is needed. Yes. And finally, for my fourth row, I can see that my temperature being high, the vehicle needs maintenance, and I'm having one yes here. So I can say that 3 rows I'm having with a particular category. And the last one, when my temperature is high, I can find that the vehicle does not need maintenance. It's given by no. So that particular term I won't consider here. So just considering my first row, second row, and fourth row into consideration, I have the value. Next slide. Next slide. So with the help of this only, I'm having my conditional probability, that is the first value calculated. Temperature being high and the vehicle needs maintenance given yes, I'm saying it to be 3/4. And when my feature selected to be oil and the value is low and given S, that is it needs maintenance, when I'm saying I can find my value to be 3/4. And similarly for the other features, mileage and noise. So this is coming up to my yes. For all the categories, S categories, I'm just finding these feature values, probability values for these particular features. And when I'm going into my second category, that is whether it needs maintenance, and I'm concluding it to be no, then in that particular sense, what are the values? I'm just categorizing. So here what I have is that in the case of feature temperature, I can see my value to be 1/3. And when it is oil, I can say that I'm having the, for oil, I can't find any value with the maintenance needed no. So I'm putting it to be 0. My favorable chances is 0. So I am putting it to be 0 divided by 3, that is 0. And similarly for my mileage, it is 1/3. And when it's going for my noise, it is having my value 0. So please put it in mind, when it is for the feature oil and noise and the combination you are having with the maintenance needed no, you are having the value to be 0. It is why in the sense there you are having no values there. Sir, kindly go on to the table. So when you see here, you will know. When it is about your considering your feature to be oil, you just take your feature to be oil, second column. So here when you're seeing your oil and when you're saying to be low, you just compare it with the maintenance column no. You can't see a value to be no there. When your oil pressure is low, you can see your data to be yes only in the first row and in the fourth row and in the sixth row also. So all the combinations regarding your low and your maintenance will be given yes in the table. So based on this particular data, I'm having this particular value. So that's why I'm given here when I'm calculating my probability for the oil, that is the selected feature, oil feature, and given the event low occurring and with respect to no, that is the need for maintenance to be no, I can say it to be 0 here. Next slide, please. Next slide. Previous slide. Yes, so that's what is done here. So here what we can see is probability of oil being selected, the feature oil is the feature, and your vehicle maintenance when it termed as no, I have no data. So that's what is given as 0. And similarly in the case of noise also, that is which is your last feature noise. So for that also I'm getting my value to be 0. Next slide. So with the help of all these values calculated, I'm just fitting into here. So as we already said, two categories being there, first one being the S category and second one being the no category. First one for the S category, when we are calculating, we have probability of event S to be happening based on the features which have already occurred. So it is nothing but 4 divided by 7. 4 is nothing but the total features. How many features are there? So it is 4. That is the favorable outcome is 4. And the total number of outcomes is 7. So I'm having 4 by 7. And the other terms 3 by 4, 3 by 4, 3 by 4. And last one, 1 is otherwise 4 divided by 4, so equal to 1. It is based on the values of those particular respective features, probability of those respective features. So you're getting this particular value, and hence you are having the term calculated as such. So finally, you have the probability for needs maintenance so much. So for your probability of needs maintenance, if suppose you are considering the category to be no, similarly, what is happening as done in the above, you just fit in the values. But one more thing which we have to note here is that here you have some more term called the Laplace smoothing. So what happens here is, since we found two features, oil and noise, and we calculated or got the value to be 0. The value 0 occurred since there was no feature there, data there, and hence we just got the value 0. In order to get rid of this value 0, there is a smoothing process done here, or otherwise called as the Laplace smoothing. So what will be done here is nothing but you will add 1 to the numerator and you will add the size of class to the denominator. So what is the class? So size that you'll be adding there, and in the numerator, that is, it is your 0, isn't it? So for that you will be adding it to be 1. So what will happen? The fraction will be rephrased as 1 by 5 here, and similarly for your noise term also it will be rephrased here. So what happens? We are just, instead of omitting these two features, oil and noise, with the help of your Laplace smoothing process, you are been fitting these particular terms also in this particular no category. So now for your probability of no, given the features, you're having your value to be 3 divided by 7. Why 3 is nothing but here, based on the features you're writing. And now all the values for your features inserted, you are getting the probability, respective probability. So when the category is need maintenance, yes, what is the value? And then when it is need maintenance, no, what is the value is given here. For the above S category, I'm having a probability of 0.2, and for the below one, it is nothing but 0.001. So this is the calculated value. Next slide. So since your value is like this, the conclusion which we come to is it is nothing but your vehicle needs maintenance. Why so we are concluding like that is that which is the highest value posterior probability, or otherwise which you are finding, it is called as the posterior probability. So that particular, based on that particular value, I can say that I am predicting my vehicle is, it will need maintenance. So that is the thing done here. So once more, when I have to reflect on the Laplace smoothing, I have to say that in order to omit or neglecting a particular feature like that, then it is saying that you're not considering that particular feature in your data set. So in order to do that, what is done is that a smoothing process is done called the Laplace smoothing in that particular situation. So you handle the problem here. What is done here is you'll be adding your 1 to the numerator and the number of class to the denominator. So it will prevent the 0 term. So you'll be considering that particular feature also. So this is done here. So when we conclude with the benefits in your real life, you can say that fleet management, it will avoid breakdowns by predicting failures before they occur. So building a model like that, we can just come to an idea what we have to do. It is also cost saving. safety, and data-driven decisions can be done here based on the historical data in order to maintain our particular vehicles. Next slide. So previously, when we dealt with the vehicle maintenance needs, here we are up to with your freight and cargo transport with Navy base. So when we dealt the same scenario with our base theorem, and when we are up to our Navy base theorem, it is nothing but we are predicting based on your features. So the objective will be whether a delivery will be on time or delayed, or whether a cargo route is will be cost effective or expensive, or whether shipment will be at risk based on the features such as theft, damage, or delay. So based on that, you can decide your route, your carrier assignment, you can schedule the process, and based on your risk management also, it will help. Next slide. So when we are saying about your Navy base, just we in order to discuss on the working, how it works, it is nothing but it is considering all the features here. For this particular example, being the feature to be your route length and the values, either it can be short, medium, or long. And when you are saying about the career reputed, either it is high, medium, or low. And the weather conditions, be it clear, rainy, and snowy. Your cargo type being perishable, fragile, and hazardous. Shipment low or high. Delivery time being morning, afternoon, or night. Weekday within Monday to Sunday, and your customs required or not required. So all these will be your features. So based on the observations, the data will be collected. Next. So your target will be based on the delivery status. So I can conclude whether it will be on time or delayed, and the cost efficiency, whether it is efficient or inefficient, and the risk level, either low or high. So how as we proceeded for the previous model, the same way when we are calculating your prior probability, conditional probability, and fitting it into your Navy base algorithm formulae, then you will be able to get your decision. So here being the training data and the features being route length, carrier, weather, cargo, and based on that, the delivery will be there. So it is based on that. Next slide. So what is being predicted here? So here when your cargo is of long route and with a medium rated carrier during a snowy weather, and whether it is perishable or not. So some scenario like that we can consider as an example. You can just build in and you can just process. So in order to find this particular scenario, Navy's classifier will be helpful, and we'll be computing for both classes. Previously, we did it whether your vehicle maintenance needed yes and vehicle maintenance needed no. So I just split it into two categories there. Similarly, when we are talking here, it will be about your whether your to complete compute your probabilities for both classes, whether it is on time or delayed. Based on that, you can just fit. So when it is on time, based on that, I'll be fitting my features, would find the prior probability, find the favorable outcomes, and based on the total number of outcomes, I'll just fit it. But this process will be done for each feature in the combination for on time. And again, when it is for a delayed manner, and again, now what I can do is that I can fix my features, calculate the values for prior probability, conditional probability based on favorable outcomes and total number of outcomes. I can do that, and I can find the values. Now, with the help of my prior and conditional probability, I can just fit it into my Navy's formulae. With the help of that, And if suppose some smoothing process is needed, also carry it down and just take the higher value for your result. So here for this particular scenario, it has been the predicted is delayed. So recommended is alternate carrier or delay shipment until the weather clears. So either you can for this particular predict, we started with a long route, a cargo will be sent for a long route, a medium rated carrier, and for a snowy weather. So the conclusion will be that either we have to alternate with another carrier or delay the shipment until the weather is clear. So that will lead to the success of the particular cargo. Next slide. So here, what are the benefits of using Navy base? So when we started, we just saw why base theorem, why Navy base, and what it is up to. So why we are going to Navy base and why it has been benefited is that when reduced delays, lower cost, better scheduling, improved reliability, and risk mitigation. So all these terms you can be benefited. So when you say about your reduced delays, it will predict the delay and avoid them proactively. So in prior, you can predict about the particular thing delay and you can take actions accordingly. So when it is lowering your cost, it is an optimal decision which will benefit the people. So that's what is given as choose optimal carrier route combination. So based on your route, also there can be a lower cost. So that is an optimal solution for it. And when you come across a better scheduling, it is nothing but assign your time slots with higher on time probabilities. So based on your time management, also here it can be perishable. So improved reliability, it is nothing but it is building trust with customers via consistent delivery. So based on the customer service, it can be of future value also. So fruitful also it will be that particular service. So based on that, it is being given as improved reliability. And when you're talking about the risk mitigation, it avoids your routes or conditions associated with theft, loss, or damage. So all these risk factors is considered whether it can be a theft or it can be a loss or damage. So based on that, also the route can be fixed or associated. Next slide. So being a comparison for Bayes theorem and Naive-Bayes theorem. So when we say it is a Bayes theorem, it is nothing but it is based on your conditional probability for, it is a mathematical formula for conditional probability. But Naive-Bayes classifier, it is nothing but a machine learning algorithm based on your Bayes theorem. So the initial step of your Naive-Bayes classifier is your Bayes theorem only. So when it is a purpose, it computes the probability of an event based on prior knowledge, initial value, which we computed when it would have been there when we computed. So what is the prior knowledge or initially what knowledge you have been knowing? With that particular assumption, we calculate for an event and we'll know the probability. Here it is used for classification task like spam detection, risk prediction. So any detection of that cause can be done over here. When it is about the scope, Bayes theorem is theoretical. It is being applied to your probabilistic event. So it is of your manual calculation and somewhat. And your Naive Bayes, it's practical and it is implemented as a model in ML. So you can, it is nothing but your model here. It is a one model in machine learning. So machine learning is a vast area where just consider this Naive Bayes classifier and the practical implementation and as now it's all of applications all over the world, it can be useful to predict decisions using this particular model. The assumptions in your Bayes theorem is no assumptions about feature dependencies. Here you won't have any features. So that's why it's given no assumptions about your feature dependencies. But in your Navy Bees classifier assumes features are conditionally independent given the class. So you can see that they are independent there. Here you can't see that. So when it is about the use cases, we can say that computing probabilities manually or in simple systems. And here it is of large data sets. So when you have one or two factors, it is easy to go with Bayes theorem. But when you are having too many and to perform, then it is best for going with your Navy Bees classifier. Next slide. I've also given why being Navy Bees instead of Bayes theorem. So it is nothing but Navy Bees automates your Bayes theorem. So Navy Bees is nothing but your Bayes theorem only. It has been applied repeatedly across many features and examples, and it is also of high speed powered by Bayes. So when you are calculating your Bayes theory manually, it can be for your 2 to 3 variables. Yes, you can opt. But when it is about your 1,000+ rows and dozens of values or features, you can just opt for your Navy Bees. Next. It'll previous slide, sir. Next. So here you can also see that it will handle your multiple features simultaneously. So using your Bayes theorem manually for multiple features, considering all these quickly becomes computationally heavy. So the work will become heavy. It will be loaded. So when it is about your ABs, it can use how many ever features wants, and based on the assumption, it will break the problem into multiple simple Bayes applications. So that is the thing. Small Bayes theorem together, it will give you your navies. That is the thing. Yeah. So when it is about your smoothing process, it will include mechanism like Laplace smoothing. So what to do? It will instead of terminating a particular feature, you can just consider all the features under study for your findings. So it is also an efficient training algorithm. So Bayes theorem on its own has no concept of smoothing or model training. So all these smoothing process or training process, it's not there in your Bayes theorem. It is nothing to tell about in your Bayes theorem. Next. So you can perform your naive Bayes with the help of all these libraries and tools. So which will be a naive Bayes being a model of your machine learning. It will be useful to classify. Concluding, then we can just know that your Bayes theorem for small, clean problems where you can compute just probabilities manually, while your naive Bayes, it is nothing but you can be given for your multiple features. You need to scale predictions. You are working with real data sets. Then for all these, then you can opt this particular algorithm. Yes. So being your naive Bayes as discussed till now, it is nothing but it will do your work faster and simpler for many features. So that's what is being considered here. So dealing with your particular topic, AI techniques like machine learning empowered by mathematics, it is just giving the details of your max foundations. All the foundations is being done. With the help of all this background work, you will be able to help the Navy Bees or any other classifier to work. I've just selected one particular thing here. So these will be the benefits empowered by mathematics, by based on the algorithm selection, based on the model performance. So we'll be able to solve the problems and find new innovative ideas and make decisions also, all the necessary decisions. effort to me. Being considering here with dealing here with my Bayes theorem and naive Bayes, I've just given some ideas. But apart from this, there are several areas where we can consider your mathematical foundations as the base or the toolkit or the foundations and make decisions. Some topics like the topological data analytics, where we can find analysis, do analysis, put it into our topology, and we can make decisions. So that is the TDA is making wonders now. So that also is been good. And in that particular process, the persistence homology or the persistent values is being done, algorithm is being calculated, and based on that, the conclusions are made. So that also is one more idea or one more way of calculating for your application oriented. Thank you all. I've done with my presentations. Any questions?
Thank you, ma'am, for informative session.
Thank you, ma'am. Thank you,
Dear,
ma'am.
dear participants, if you have any queries, kindly unmute and ask.
Good evening, ma'am.
Yes, sir. Good evening, sir.
So this is Dr. Akbar Ali from Government Arts and Science College for Women, Coimbatore.
Yes, good evening,
I
sir.
have a short question. While considering the data sets with missing values or with some noise, how
Yes,
does
sir.
this Navy-based theorem work over there?
Tell me, sir.
Got my question now? Now, actually, the real data sets with noise or missing values, how do we apply the Navy-based theorem?
Sir, yes, sir. When it is missing values, you are not just omitting a feature, and for that particular thing, you are dealing with a Laplace smoothing formulae.
Okay.
So in your Navy Bees, we are having one particular technique called the Laplace smoothing. So while using that, just without avoiding your term, you're making assumptions and you're just considering that particular feature also for your study.
Okay.
But that particular thing we are not doing in Bayes theorem.
The Laplace smoothing we do over there.
Yes, sir. That is the particular technique involved there.
Okay, ma'am. Thank you, ma'am. Excellent presentation.
We sincerely thank Dr. Albinaa for her enlightening session on AI techniques like machine learning empowered by mathematics. Your expertise and perspective have enriched our understanding. We value your contribution and time. We also extend our heartfelt appreciation to all the participants for your active engagement and enthusiasm throughout the session. Your presence and inputs made the discussion more meaningful. Thank you, ma'am.
Thank you, ma'am.
The
Thank you all.
feedback link is shared in the chat box. Kindly fill out the form before leaving the session. Thank you once again, and we look forward to your participation in the upcoming days of the FDP. Thank you, ma'am.
Thank you, ma'am. Thank you
Thank
all.
you all.